Interpolation. Interpolation is the process of estimating unknown values between known data points using the average growth rate. Example: in the fall of 2007, 38.2% of college freshmen in the United States believed that marijuana should be legalized. In the fall of 2011, that figure was 49.1%. Use these figures to estimate the percentage in the fall of 2008 and to estimate the percentage in the fall of 2009. We can compare this to the actual figure for the 2009, which was 45.6%. What does this say about how the growth rate and the percentage varied over the time? Notice that for the years 2008 and 2010, it is unknown what portion of students believe that marijuana should be legalized. Somehow we have to use the years 2007 and 2011 to estimate this. The change in the dependent variable from 2007 to 2011 is 4 years. The change in the dependent variable over the same period is 10.9 percentage points. Now let's find the average rate of change using the formula that we saw earlier in this PowerPoint presentation. We have to compute the change in the function, which we did, and divide it by the change in the independent variable. This results in 2,725,000. That means that on average, the increase was 2,725,000 percentage points each year over this period. The year 2008 represents 1 year of increase from 2007. So the percentage in 2008 was about whatever was the percentage in 2007 plus 1 year of increase. That results in 40.9%. The year 2009 represents 2 years of increase from 2007. So we start with percentage in 2007 plus 2 years of that increase. And that results in 43.65%. Our estimate of 43.65% is less than the actual figure of 45.6%. This means that the growth rate from 2007 to 2009 was less than it was from 2009 to 2011. Example: SARS is a viral respiratory disease. There was a serious outbreak initially in China from November 2002 to July 2003. There were 8,096 known cases and 774 deaths worldwide. Calculate the average growth rate of cases from March 26 to March 31st. Use your answer from part 1 to estimate the cumulative number of SARS cases by March 28. The actual cumulative number on March 28 was 1,485. What does this say about how the growth rate varied over time? Here's a table that gives us the dates in March and April, and also the number of cases of SARS. The independent variable here is days, the date. The function, the dependent variable, is the number of cases. The average rate of change is the difference in number of cases divided by the difference in time. The number of days between March 31st and 26 is 5 days. That's the figure in denominator. The independent variable is in the denominator. And the number of cases, the difference in number of cases, is 1,622 minus 1,323. That goes in the numerator, the change in the function values. The quotient is 59.8. The average growth rate from March 26 to March 31st is 59.8 new cases per day. There were 1,323 cases on March 26. And from what we computed earlier, we expect to see about 59.8 new cases on March 27th. And that figure is going to grow by another 59.8 new cases on March 28th. So the estimated cases on March 28th are equal to cases on March 26th plus 2 times the average new cases per day, because March 28th is 2 days away from March 26th. So we estimate that there will be 1,402.6 cases on March 28th. Our estimate using interpolation is relatively good, but it's slightly lower than the actual value of 1,485. Extrapolation is a process of estimating unknown values beyond known data points using the average growth rate. Right, so to extrapolate is to estimate unknown values beyond known data points. In contrast, interpolation is the process of estimating unknown values between known data points. So extrapolation is outside of known data points. Interpolation is between known data points. Here's an example. The following table shows the average age in years of first-time mothers in a given year. First row is the year, second row is the average age. The year is independent variable, average age is dependent variable. Estimate the average age of first-time mothers in 2007. Predict the average age of first-time mothers in 2015. Predict the average age of first-time mothers in the year 3000. Explain why the resulting figure is not to be trusted. Notice that in part 2, we're to predict the average age of first-time mothers in 2015. This is outside of the data points. It's not between 1980 and 2010, but outside of these years. So we're extrapolating. If we were to find the average age of a first-time mother in 1991, we would be interpolating. Solution. We estimate the average age in 2007 by interpolating. The average growth rate between 2000 and 2010 is given by the average growth rate formula. In the numerator, we have two adjacent function values divided by the difference between two adjacent values for the years. This is equal to 500ths per year. The average age for first-time mothers increased at a rate of 500ths per year over this decade. Now, 2007 is seven years away from 2000. So what we can do is multiply this average increase per year by 7 and tag that on to the average age in 2007. So we have 24 9/10 plus 7 times the average growth rate, and that results in 25 1/4 years. In part 2, we estimate the average age by extrapolating. The growth rate between 2000 and 2010 that we found in part 1 was 500th per year. So we assume that the increase of this increase of 500th per year is going to be the same for the next 5 years. And 2015 is 5 years past 2010. Therefore, we can take the age at 2010 and add to it 5 times the average growth rate. 25 4/10 plus 5 times 500ths, that's equal to 25 6500ths years. Part 3 is exactly like part 2. We're going to extrapolate again because 3000 is outside of the given dates that we're having a problem. Again, the average growth rate from 2000 to 2010 is 500th per year. 2010 and 3000 are 990 years away from each other. Assuming that this growth rate continues for these 990 years, the age of first-time mothers, the average age of first-time mothers will be the average age in 2010 plus 990 times the average growth rate of that age per year. That results in 74 9/10 years. So we project that in 3000, the age of a first-time mother is 75 years. This is unreasonable. This is one danger of extrapolating. If you go too far away from the data, you will get unreliable results.